Hi, in this video I want to talk about the Pythagorean theorem and its converse. So most people I think are probably aware of the Pythagorean theorem that a squared and b squared is equal to c squared. If you have a right triangle, a squared and b squared is equal to c squared. Now there is a law of cosines, which I think is much more useful. If you know the law of cosines, it's c squared is equal to a squared plus b squared minus 2ab cosine theta, where theta is the included angle. And this works for all triangles. So if you have say a triangle like this is your angle, call this your A, this your B, and this is your C. And the Pythagorean theorem is really just a special case of the law of cosines, because for 90 degrees, the cosine of 90 is 0, and this whole term goes away, and you're just left with the Pythagorean theorem. Now, more than finding side lengths, the Pythagorean theorem can be used to test what type of a triangle you actually have. So, if a squared and b squared is equal to c squared, your triangle is a right triangle. But if a squared and b squared is less than c squared, then you have an obtuse triangle. And if a squared and b squared is greater than c squared, you have an acute triangle, which means all angles are less than 90 degrees. So not only can you tell if you have a right triangle based on the side lengths, you can also tell what kind of a triangle you have if the sides squared added together are less than c squared, that angle is an obtuse angle. And if a squared and b squared is greater than c squared, then all the angles are less than 90 degrees. So let's look at some problems that go with this. So this sheet comes, I think, from an honors geometry text. I think it's from the Jurgen text. So let's see. Example 1. If a triangle is formed with side lengths having the lengths given, is it a right triangle? So what they want us to do here is, and what you have to do is always look for the biggest one, the biggest number. That's going to be your C. So what you want to do is check, is 16 squared plus 30 squared equal to 34 squared? If it's not, you can actually do more than just tell if it's a right triangle. You can actually tell what other type of a triangle it might be if it's not right. So let's see what they do here. 16 squared and 30 squared comes out to be 1156, and 34 squared is 1156. Therefore, this is a right triangle. So we got like a 34, a 30, and a 16. Let's look at 3, 4, 6. 3 squared is 9, 4 squared is 16, 6 squared is 36, 9 and 16 is 25. 25 is less than 36. So we have the case here where a squared and b squared is less than c squared. This triangle is not right, but more than it not being right, it is obtuse. So not to scale, but I know that this triangle must look something like this. This is going to be the 6, one of these is a 3, and one of those is a 4. So you can see 1, 7, and 7. Now this is going to be a problem here. You can't really have a triangle with two side lengths the same, but let's check it out. 1 squared and 7 squared is 50. And you have 50 versus 49. A squared and b squared is greater than c squared. If a squared and b squared is greater than c squared, that would be an acute triangle. Actually, what we have here is an isosceles triangle because of the two 7s. And I didn't draw it to scale, but this would have to be a 1. And you can see that all these angles are going to be less than 90 degrees. So you have an acute triangle. So that's basically it for the converse of the Pythagorean theorem. Let's talk a little bit about Pythagorean triples. This is kind of maybe a shortcut. The basic pattern that we all use quite a bit is 3, 4, 11. 5, 12, 13 is a pattern that's used on more standardized tests like the SAT, because it's not so obvious as a 3, 4, 5. And then the other thing that they're trying to get across here is that multiples of this 5, 12, 13, or 3, 4, 5 are also Pythagorean triples. And so 5 squared and 4 squared is 25. Now 3 squared and 4 squared is 9 plus 16, which is 25, and 5 squared is 25. So these are the smallest integers that can make up a right triangle. But multiples like 6, 8, and 10, 9, 12, and 15 are all basic 3, 4, 5 type Pythagorean triples. So if you can recognize, like let's say you're given a 12, 16, 20 triangle. If you look at these, okay, 4 goes into each of these, factor of 4 out. You've got 4 times 3, 4 times 4, and 4 times 5. You can see that this 12, 16, 20 basically reduces to a 3, 4, 5 ratio, which lets you know right away without going through the process of using the Pythagorean theorem that you have a right triangle. 5, 12, 13 is, occurs a lot in examples in the book or in problems in the book or on standardized tests because it's not so obvious. But 5 squared is 25, 12 squared is 144, so together those add up to 169, and 13 squared is also 169. So 10, 24, 26, 15, 36, 39. If you look, let's do a 20, 48, 52. So let's say you're given this and you're asked, is this a right triangle? Okay, you got two options. You take a calculator, you can do 20 squared and 48 squared, see what the sum is, and then check that out and see how that relates to 52 squared to see if it's a right triangle or not. Or, since these numbers are all have common factors, let's find the biggest common factor that goes into each one of these, and 4 times 5 makes 20. 4 times 12 makes 48, and 4 times 13 makes 52. So this reduces to a basic 5, 12, 13 set of side lengths. And if you remember 5, 12, 13 is a Pythagorean triple, you can see right away that you do have a right triangle without going through the process of using the Pythagorean theorem.